Good morning, students. Myself, Vijay Shankar from ECE Department, Chevrolet Engineering College. Today, I am going to discuss about the Smith chart construction in the transmission lines 2. Already, we discussed and derived the expressions to get the normalized from the normalized impedance. ZR is equal to ZR by the Z0, R circles and the X circles, where R is a resistance and X is the reactance. Okay. Now you can find the center and the radius of gamma R and the gamma I. Gamma R and the gamma I for R circles and the X circles. Okay. So once again, we go for what is a Smith chart and how we can construct the Smith chart briefly. The Smith chart is a polar plot of reflection coefficient in terms of normalized impedance R plus Jx R. A Smith chart is a graphical plot of normalized resistance and the reactance in the reflection. Resistance and the reactance in the reflection. Okay. It consists of two sets of orthogonal circles. It consists of two sets of orthogonal circles which represents the values of normalized impedance. One set of circles represents the resistive component R, called as R circles. Another set of circles represents the reactive components X, called as X circles. And the construction, you see here, the circle what we are showing here, it is a S is equal to 1. At the reflection coefficient is a 0, and if reflection coefficient is equal to 1, the S is equal to infinite. Okay. The real axis, the reflection coefficient R, and the reflection coefficient in the imaginary axis. Okay. The construction is the Smith chart is constructed with a circle of radius. Reflection coefficient is less than or equal to 1, as shown in the given figure here. The construction of the Smith chart is based on the relation of reflection coefficient is equal to. Actually, in the transmission line, we are representing the reflection coefficient is a K. Okay. Or it is a gamma also. The reflection coefficient is equal to ZR minus Z0 by ZR plus Z0. And its magnitude is in the polar form, the magnitude, reflection coefficient, and angle theta gamma. And in the rectangular form, the gamma R plus J into gamma I, where the gamma R and gamma I are the real and imaginary part of the reflection coefficient gamma. For the load impedance ZR, the normalized load impedance is given by ZR is equal to ZR by Z0, what I said, that is equal to R plus Jx. To avoid the confusion, the ZR is equal to ZR by the Z0. Actually, it's a small ZR and it is here representing the capital ZR, small ZR, and it is a capital. So to avoid that confusion, you can assume that it is a Zn is equal to ZR. So Zn is equal to ZR by the Z0, that is equal to R plus Jx. And the reflection coefficient in the rectangular form, gamma R plus J into gamma I is equal to ZR minus Z0 by ZR plus Z0. In the above equation, you can take the common of Z0, you'll get ZR by the Z0 minus 1 whole divided by Z0, and denominator also you can take the common of ZR, Z0, ZR by the Z0 plus 1. So Z0 get cancelled, and the ZR by Z0 we assume is a normalized impedance Zn. So reflection coefficient in the real term plus J into the reflection coefficient imaginary is equal to, in terms of the normalized impedance, Zn minus 1 by Zn plus 1. Okay. So now you can cross multiply the function Zn plus 1 multiplied with the gamma r plus J into gamma I is equal to Zn minus 1 and Zn gamma r plus J into Zn gamma I plus gamma r plus J into gamma I is equal to Zn minus 1. Zn minus 1. So take the Zn as a common, where we can bring that as a Zn towards the left side. Zn, and you can bring all that is in the right hand side, or 1 minus gamma r minus J into gamma I. These two are two in the left hand side is equal to, bring this minus 1 into the left hand side, gamma r plus 1 plus J into gamma I. From this, Zn is equal to 1 plus gamma r plus J into gamma I whole divided by 1 minus gamma r minus J into gamma I. So you got the Zn is equal. Okay, 1 plus gamma r plus J into gamma I, 1 minus gamma r minus J into gamma I. Rationalize the function. Rationalize here. See, 1 plus, we got 1 plus gamma r plus J into gamma I whole multiply with 1 minus gamma r. In the denominator, there is a minus is there. We can plus here J into gamma I whole divided by 1 minus gamma r. This is Zn is equal. So normalized impedance Zn is equal to 1 minus gamma r minus J into gamma I multiplied with 1 minus gamma r plus J into gamma I. Okay. So in the numerator, you can multiply 1 minus or 1 plus 1 minus gamma r plus J into gamma I plus multiply with 1. Then after it is a gamma r minus gamma r square plus J into gamma r and gamma I. Okay. With this gamma r with total function, gamma r minus gamma r square plus J into gamma r and gamma I. And with this third term, J into gamma I minus J into gamma r and the gamma I. And the last term J into J is a J square. J square into gamma I square. Okay. And in the denominator, it is an A minus B into A plus. What is the A here? 1 minus gamma R whole square. A square minus B square. Here the B is the J gamma I. J square is equal to minus. Then it becomes a plus gamma I square. Okay. that is equal. See, there is any cancellations in the numerator. So plus j gamma r and minus j gamma I and gamma I. You got it? So remaining functions plus gamma r and here the minus gamma r. Both are get cancelled. And still anything is there. So what is the remaining? 1 my plus j into gamma I minus gamma r square plus j into gamma I, and j square is a minus gamma I square, gamma I square, whole divided by 1 minus gamma r square whole square plus gamma I square. Okay, I can see here in the numerator gamma I, j gamma I will become as a 1 plus 2j gamma I, 2j gamma I, and minus gamma I square and minus gamma r square whole divided by 1 minus gamma r square whole square plus gamma I square, that is equal to. So in the numerator there is a 1 plus gamma I square is there, gamma I square, and 1 plus 2j gamma I. You can write this function as now here to write this function as 1 minus gamma r square minus gamma I square whole divided by 1 minus gamma r square whole square, gamma r minus 1 minus gamma r whole square plus gamma I square and plus j into 2 gamma I whole divided by 1 minus gamma r whole square plus gamma I square. So Zn is nothing but r plus j into x, r plus j into x. What is r now? The real term, where x is the imaginary term. So see here, we got r is equal to 1 minus gamma r square minus gamma I square by 1 minus gamma r whole square plus gamma I square. This is a term we have is a x plus j into, or sorry, this the term is a real term is r plus j into x. X term is 2 gamma I by 1 minus gamma r whole square plus gamma I square. And rearrange these two functions. Rearrange these two functions to get. So up to this is okay. That we will get the r and the x. Then how we get the center values of r by 1 plus r and 1 by 1 plus r. Okay, I will explain this in there. If r is equal to, now I got r is equal to 1 minus gamma r square minus gamma I square whole divided by 1 minus gamma r whole square plus gamma I square. Now cross multiply this function r into 1 plus gamma r square plus 2 gamma r plus r into gamma I square is equal to 1 minus gamma r square minus gamma I square. I'm multiplying all the functions r plus r into gamma r square plus 2r into gamma r plus r gamma I square and bring these two functions towards the left side plus gamma r square plus gamma I square is equal to 1. Is equal to 1. Okay. Now we can take the common of gamma r function, or you can simplify the function as gamma r. You can take the gamma r square. Gamma r square you can take as a common. Here the second term is a gamma r square, there is a r, and here the last term is a gamma r square plus 1. And these two terms will complete it. Then we have another function. This is a 1 minus gamma r. So sorry, here you have to write this up minus my students. So 1 minus gamma r square means a plus square plus b square minus 2a. This also will get the minus 2ab. Okay. So you can write that function minus 2r gamma r. This function is also completed. And the remaining can take the gamma I as a common plus gamma I square is a common. Here the gamma I square is a 1 and r 1 plus r. Now these two functions also completed. And only remaining there is a r is there. Bring that r in the right hand side, 1 minus r. So all the terms completed here. Now divide all the terms with the 1 plus r. Divide all the terms. Here the 3 terms in the left hand side, 2 terms is there in the right hand side. So divide all the terms by 1 plus r or r plus 1. So after dividing that, it is a gamma r square minus 2 into r by 1 plus r into gamma r plus, and here also you can divide with 1 plus r, it's a gamma I square is equal to 1 minus r by 1 plus r. So listen carefully, my students. I divided the term, divide both sides with 1 plus r. Okay. Now to see here, gamma r square minus 2 into a and b is there. To write this as a minus b whole square formula, the b square you have to require r by 1 plus r whole square. So add both sides with my 2 into gamma r and r by 1 plus r. I'm adding here r by 1 plus r whole square in the left hand side. Similarly, in the right hand side also you can add the term 1 plus R plus R by 1 plus R whole square. Both sides we add the R by 1 plus R whole square, because it is in the form of A square minus 2 A and the B and B square. From these three terms, you can write this function as gamma R minus R by 1 plus R whole square plus gamma I square is equal to, you can now simplify here, the denominator it is 1 plus R whole square. Now the denominator is 1 plus R means you can multiply with 1 minus R with 1 plus R and plus R square. Simplify the numerator and write this function as gamma R minus R by 1 plus R whole square plus gamma I square is equal to, now it is the form of A minus B into A plus B. So A square minus B square plus R square whole divided by 1 plus R whole square. Now in the numerator plus R minus R get cancelled, and finally you can write this function as gamma R minus R by 1 plus R whole square, and you can also write this function as gamma I minus 0 whole square. 0 whole square means A square minus B square plus B square minus 2AB, both are the zeros. Only you get the gamma I square is equal to, after cancellation of R square minus R square, 1 by 1 plus R whole square. Okay, my dear students, see this is same as of gamma R minus R by 1 plus R whole square plus gamma I square and 1 by 1 plus R square. Means it having the center as a center, if it is considered as a H is equal to R by 1 plus R and K is equal to 0, and with radius A is equal to 1 by 1 plus R. Okay, the center H comma K is R by 1 plus R comma 0, and with the radius of 1 by 1 plus R, we'll get the R circles. R circles, nothing but it is a polar circles. Got it, my dear students? So see here, the above equations are in the form of the equation of circle x minus h whole square plus y minus k whole square is equal to a square. And in the equation, this is equation 6, is an R circle, it's a resistance circle, center at gamma R and gamma I, because here the gamma R and the gamma I is there. Its center is R by 1 plus R by 1 plus R comma 0. And its radius is, what is its radius? 1 by 1 plus R. Okay. So with this center and the radius of 1 by 1 plus R depends upon the R values, we'll get the circles like this. With center 1, 2 and so on like this, with the radius of 1 by 1 plus R. These are the R circles. Got it, my dear students? How we got this equation from R is equal to 1 minus gamma R square minus gamma I square by 1 minus gamma R whole square plus gamma I square. Okay. Similarly, now you can derive another equation, x is equal to. So x is equal to, we got the 2 gamma I by the 1 minus gamma R whole square plus gamma I square. And it is also simplified now like this: 1 minus 1 plus gamma r square minus 2 gamma r plus x into gamma I is equal to 2 gamma I. Got it, my students? So multiply with the x here, x plus x into gamma r minus 2x into gamma r plus x into gamma I minus 2 into gamma I is equal to 0. So 2 gamma I is also, you can bring that in the left hand side. Now you can take divide all the functions. Divide the function with x totally. So 1 plus gamma r square, my students, here 1 plus gamma r square minus 2 gamma r plus gamma I minus 2 by x into gamma I is equal to 0. Got it? Divide the equation with the x. So first three terms, the first three terms you can write as gamma r minus 1 whole square. So a square minus b square, not the minus, plus b square minus 2ab plus, and here also gamma I, it is a square, my dear student, sorry, gamma I square and minus 2 into gamma I, and 1 by x is there. So let us use a b. So you can add and subtract the 1 by x whole square plus 1 by x whole square is equal to 0. It's a minus, my dear students, not the plus. Add and subtract. Okay. Now here gamma r minus 1 whole square plus, and these three terms you can write as gamma I minus 1 by x whole square. So because gamma a square plus b square minus 2ab, and this minus 1 by x square you can write in the left hand right hand side 1 by x square. Now here also you can see the gamma r and the gamma I as x and y. H and k is the center. What is the center here? 1 comma 1 by x, 1 comma 1 by x, and with the radius a is equal to 1 by x. The center a comma h comma k is equal to, you got 1 comma 1 by x. So see here the gamma r minus 1 whole square is equal plus gamma I minus 1 by x whole square is equal to 1 by x. Got it, my dear students? This is the same we got in this equation with the center of 1 by 1 comma 1 by x and with the radius as 1 by x. You'll get the x circles. Okay. Similarly, is an x circles reactance circle, the center at 1 comma 1 by x and with the radius of 1 by x. You'll get the half circles like this. Above the values all it is a positive values, and below the values all it is a negative values in the imaginary coefficients. In the Smith chart, my dear students, this is a bottom line as x is equal to 0. If suppose if any circle R circle is combined with the x circle, means it is in the rectangular form x plus j into r. Okay, x plus r plus j into x, sorry, r plus j into x. So the above, that is r plus j into x, and in the below this line is totally all the values are r minus j into x in the Smith chart. So we'll get the circles like this. combining of the two functions x and r circles. If any point is here, that point is r plus jx. If there is any point in this r minus jx, the below the bottom line. Okay, let us consider this is a baseline. Above the baseline r plus jx, and below the baseline is r minus jx. Okay, so with this derivation, with the center of 1 comma 1 by x and the radius 1 by x, we will get the x circles. And with the center of r by 1 plus r comma 0, and with the radius of 1 by 1 plus r, we will get the r circles. Got it, my dear students? Now you can see the applications of the Smith chart. Applications of the Smith chart, my dear students. To find the parameters of mismatched transmission lines, and to find the normalized impedance from normalized impedance, and also the vice versa, the normalized impedance from normalized impedance. And also you can find the voltage standing wave ratio, yes, for a given load impedance, and design the steps for impedance matchings, and find the reflection coefficient also. These are the parameters you have to find out using the Smith chart with the R circles and the X circles. These are only the applications also. The Smith chart can be used to find the parameters of mismatched transmission lines, and find the normalized impedance from normalized impedance, and find the normalized impedance from normalized impedance, and also find the standing wave ratio for the given load impedance, and design the steps for the impedance matching, and find the reflection coefficient also. And steps for the solving of Smith chart problems, if any given. So what are the steps you have to use here? Find the normalized load impedance. Zn is equal to Zr by the Z0. In the example, they have to give load impedance and the input impedance. The ratio between of these two is a normalized impedance. Okay, that is nothing but R plus Jx. You'll get the normalized impedance. Mark the normalized load impedance on the Smith chart with the R and the X circles, where R is a circle, so with center of R by 1 plus R comma 0, and with the center with the radius of 1 by 1 plus R. Okay, assume a point P at the intersection of R and the X circles. See, if the given will get the real term and the imaginary term, assume that the point is a P, and draw the line from the origin to the point P, and extended the point P to the point Q. Okay, is on the Smith chart. See what I explain here by using the Smith chart. See, this is a Smith chart circle, so inside. See, this is a Smith chart is look like after combining of X circles and the R circles. So first of all, you can, whatever they given, see, this is a point P. This is a point P, my dear students. To get this point P, the given terms Zn is equal to nothing but R plus J into X. That is a normalized impedance Zr by the Z0. If they given the Zr by the Z0, you can find out the terms here, the real term and the imaginary term. Mark this as R circle and X circle. let this a point is a R circle and X circle. Say that is a point P. And now join with the center of origin O, and this point P is extended on the circle. Say that point Q. Okay, this is a Q here. Up to that, you can extend. What they are saying here, for the normalized load impedance on the Smith chart, R and X circles, assume the point P at an intersection of R and X circles. The intersection of R and X circles is a point P. Draw a line from origin to the point P and extended the point P to the point Q. Extended the point P to the point Q. Means first of all, you can join these two, 0 to P. Then this point is extended up to the point Q. Is a Q here. And then observe the reflection coefficient magnitude. The magnitude of the reflection coefficient is the distance OP, whatever the distance we got in this here, the distance OP by, find the distance from here, OP by, and PQ, the ratio between of OP distance to the OQ, sorry, here it is a OQ, my students. So you have to find out OQ. Okay, the ratio between of OP to OQ will get the magnitude of the reflection coefficient. Magnitude of the reflection coefficient. Okay, and then here, these are, I said that is a bottom line, is at the 0. This is a bottom line, and by using the protractor, you can find the angle here. That angle is nothing but theta gamma r. Okay, we get the magnitude of gamma is equal to the distance of OP by the distance of OQ. We'll get some magnitude here. Then after, you can find the theta, the angle here, the reflection coefficient angle. Okay. Now the magnitude of reflection and angle of the reflection will get and convert that into the rectangular form. So the measure of the reflection angle theta. So the reflection coefficient is equal to the magnitude of gamma reflection and angle of reflection. Take the OP radius. Okay, take the OP radius and draw a circle at center O with OP radius. So in this, take this distance by using the compass with the center of O, draw a circle here. Draw a circle. Sorry. So draw a circle with the radius of OP. Let us, this is a circle we got with the OP radius. And point where it is crosses this bottom line, that is nothing but S. Standing wave ratio or voltage standing wave ratio. Got it, my students? See here, they're saying that take the OP radius and draw a circle at center O with OP radius. Measure the standing wave ratio from point O to the point S. Measure the distance here. So distance from the O to the S. Whatever the value here, the distance, that is nothing but the standing wave ratio. Yes, sir. Measure the standing wave ratio from point O to the point S. So by using this, we got the magnitude of the reflection and angle of the reflection coefficient, and with the radius of OP, you can draw a circle with the center of origin. You'll get the distance from O to S is the standing wave ratio. Find the normalized impedance using the length of the transmission line. Length must be in terms of lambda. That lambda is nothing but 722 degrees, and lambda 2 is 360 degrees, and lambda by 2 is in terms of the lambda only, that is a 0.5 the lambda, half of that point. Okay, I will show that. See, in this there is a circuits we have. There is a circles like this. This part is a lambda by 2. Lambda by 2 means 360 degrees. Lambda by 4, 180 degrees. Okay. And what is a lambda here? Lambda is nothing but lambda is equal to 720 degrees. Lambda by 2 is 360 degrees. Got it, my dear students? And a lambda by 4, what is a lambda by 4? It's a half and it is a quarter, is 180 degrees. Okay, so it is a lambda by 4 lengths. So 180 degrees and it is a 180 degrees line. Got it, my dear students? Is always towards the generator G. The arrow mark is in the clockwise direction. Towards the load is anti-clockwise direction. Okay, my dear students. This inside there is a circles. Have to find out the V maximum and the V minimum towards this. Okay, here there is a V maximum. You'll get the V minimum, the voltage maximum and the voltage minimum values. Okay, why it is a maximum towards this one and why it is a minimum towards means X and R circles here. The X circles and the R circles, both are the zero values towards this side. And towards this side, both increasing the value 0 and so on, it is increasing. We'll get the value here up to the infinite. The X value and the R circles is a infinite. So you'll get the V maximum towards this side and V minimum towards this side. The V minimum. Got it, my dear students? So lambda by 2 is a half and lambda is a 720 degrees. Lambda by 4 and here the 90 degrees. Lambda by 8 is 90 degrees. Sorry, 90 degrees. Got it, my dear students? 3 lambda by 8 is a 270. This is a 270 degrees. And this is a 180 degrees. And this is a 90 degrees. And it's a 360 degrees. Again, these are 0, 1. 0, 90, 180, 270, like this, towards the generator. Got it, my dear students? Lambda by 8, where the lambda is in terms of the length of the transmission line, or also in terms of the degrees. Got it? So lambda is a 720 degrees, lambda by 2 is a 360 degrees, and that is in terms of the lambda only, the 0.5 lambda. Okay, to find the normalized impedance by moving from Q in clockwise direction. So I told that is a clockwise direction is towards the generator, anti-clockwise direction is towards the load. So to find the normalized impedance by moving from Q in clockwise direction with a given transmission line. Draw a line from 0 to the given length of the line. Mark the point A at the intersection of a SWR circle. The input impedance, the line. Got it, my dear friends? In this way, you have to find out all the parameters what we are discussed in the applications. That applications is if it is used to find the parameters of mismatched transmission lines, normalized impedance, normalized impedance, voltage standing wave ratio, and stubs, and the reflection coefficient. Got it, my dear students? These are the 10 points, 10 steps you have to use to draw SB charts, and you have to find out the parameters. Got it? Or we also call it as a applications.